Welcome grade 12s to STEM in Action's Boost series. I'm V Guyan and this is Acids and Bases Part 2. First thing we're going to talk about today is our conjugate acid-base pairs. When an acid, for example HA, loses a proton, its conjugate base will be the A minus, so what is left over when the proton is gone. When a base, A minus, accepts a proton, its conjugate acid is HA, so what is formed when it accepts that proton. These two are a conjugate acid-base pair. So we have nitric acid with the hydroxide ion forming the nitrate ion and water. So we know that nitric acid is our acid. When nitric acid loses the proton, it donates the proton, what is left is our nitrate ion, that is our conjugate base. If our OH minus, our base, accepts that proton, it becomes water, which is therefore our conjugate acid. What is ampiprotic? It is a substance that can either act as an acid or as a base. For example, water. Water can accept a proton to become the hydronium ion and therefore acting as a base, or it can donate a proton becoming OH minus and therefore acting as an acid. So there you can see in our little picture that if water accepts the proton, it goes to the left and it becomes the hydronium ion, whereas if it donates a proton, it then becomes the hydroxide ion on the right. Some other examples of ampiprotic substances are HCO3 minus or H2PO4 minus. A rule of thumb here is a substance that has a hydrogen but also has a negative charge. If it has the hydrogen, it's able to donate a proton, thereby being an acid, and if it has the negative, it's able to accept a proton, thereby being a base. Let's have a look at some application questions on these two terms. Let's have a look at November 2018, question 7.1. Question 7.1 says sulfuric acid is a strong acid present in acid rain. It ionizes in two steps as follows. And there they give you the two equations. 7.1.1 asks us to define an acid in terms of the Lurie-Bronsted theory. We did that in part 1. So I already have my answer down here for us. 7.1.2 says write the formula of the conjugate base of H3O+. Right. So, H3O plus is an acid, and so if it donates a proton, what are we going to form? That would be our conjugate base. So, if we lose a H plus from H3O plus, we're going to be left with simply water. We can also have a look at that here in our formula. If we look, there's H3O plus, so the reaction is going to be going that way for it to lose H plus, and when it loses H plus, what are we left with? H2O. 7.1.3 then says, write down the formula of the substance that acts as an ampholyte in the ionization of sulfuric acid. So an ampholyte, that's another word for ampiprotic, and so we're going to have a look at what acts as an acid and as a base. So if we have a look at our two equations, over here we have our acid, very clearly, it donates a proton to the water. So over here we have an acid and this is a base. But if we come down here, HSO4 minus, now it loses that or donates that hydrogen to the water to form H2O plus, and we're left with SO4 minus. So our HSO4 minus is our ampholyte. Remember our rule of thumb, if it has a negative and a hydrogen, it's a good chance that it will be ampiprotic or an ampholyte. Right, let's have a look at another application question. We'll have a look at question 7.2 from November 2019, paper 2. Question 7 says a hydrogen bromide solution, HBr, reacts with water according to the following balanced chemical equation. The value of Ka for HBr is 1 times 10 to the 9. Question 7.1 we already answered in part 1. So we'll move on to question 7.2. Question 7.2 asks us to write down the formulae of the two bases in the above reaction. So if we have a look at our reactants, we clearly know that HBr is an acid, and so therefore that makes water our one base. So we can write that down. And we also know that once an acid loses its proton, it has a conjugate base. And so if we look at, if this had to lose the hydrogen, what's left is our Br minus, and so Br minus is also a base. Right, that brings me to the end of those application questions. Let's have a look back at our PowerPoint, and we'll come back to these exam questions a bit later. Right, on to neutralization reactions. Neutralization reactions happen between an acid and a base. We have two forms of that. We can have an acid and a base, a hydroxide base, that will form a metal salt and water. For example, hydrochloric acid reacting with sodium hydroxide to form sodium chloride and water. We can see that our metal salt comes partly from our acid and partly from our base. Your positive ion of your metal salt will always come from your base, and your negative ion of your metal salt will always come from your acid. That's because what's left over in the acid and the base joins together to form our water. Our H plus from our acid and our OH from our base form our water. We can also have an acid and base reaction where the base is in the form of a carbonate. And here we'll also form a metal salt and water, but in addition to that, we'll also form carbon dioxide. And so an example of that would be sulfuric acid reacting with sodium carbonate to form sodium sulfate, water, and carbon dioxide. Again, our positive ion of our metal salt comes from the positive ion in our base, our carbonate, and the negative ion comes from the negative ion in our acid. Couple of definitions that come up when we're talking about neutralization reactions. Neutralization reactions generally take the form of a titration, and you can see how a titration is done in our titration experiment episode. In a titration, we have something called the equivalence point, and that is the point where the acid or base has completely reacted with the base or acid, and so everything has been used up. On the other end, we also have something called an end point of a titration, and this is the point where the indicator changes color. These two definitions are similar, but they are not the same. Next, we need to talk about hydrolysis. Hydrolysis is the reaction of a salt with water. The first type of salt we get is a neutral salt. A neutral salt is formed when we react a strong acid and a strong base. And then the pH of the solution and the pH of the salt that is formed is around 7. So what would happen? We will have something like hydrochloric acid reacting with sodium hydroxide, and we get a salt of sodium chloride. That salt of sodium chloride, if it had to ionize, it would have a sodium ion and a chloride ion. Those both come from a strong acid and a strong base. And we know the definition of a strong acid or a strong base is that it ionizes or dissociates completely, which means it wants to stay in its ion form. And so, remember, hydrolysis is the reaction of a salt with water. Because those ions want to stay in solution, they are not going to react with water, and therefore the salt from a strong acid and base does not undergo hydrolysis. However, on the other hand, we can have a reaction between a strong acid and a weak base. In that case, we're going to get an acidic salt, and the pH of the salt will be less than 7. It will be acidic. For example, we could have sulfuric acid reacting with ammonia to form ammonium sulfate, and that ammonium sulfate, the ammonium sulfate salt will ionize in water to form ammonium and sulfate ions. The sulfate ion comes from our strong acid, our sulfuric acid, and therefore it wants to stay in its ion form and will not undergo hydrolysis. However, the ammonium ion comes from a weak base. It comes from the ammonia base. And therefore it does want to undergo hydrolysis, and it does react with the water. And so we get the ammonium ion plus water reacts to form ammonia plus the hydronium ion. So we can see that we get an increase in the hydronium ion, and if we have something that's creating more hydronium ions, we therefore know that it is going to be an acidic solution, and therefore it is an acidic salt. The last case we can look at is for a weak acid and a strong base. When we have a weak acid and a strong base reacting, we're going to get an alkaline salt or a basic salt, and the pH there will be greater than 7. For example, if we have hydrogen fluoride plus sodium hydroxide, we're going to get sodium fluoride as our salt. The sodium fluoride salt will ionize in water to form sodium ion and fluoride ion. The sodium ion comes from a strong base and therefore wants to stay as an ion. But the fluoride ion will react with water and undergo hydrolysis to form hydrogen fluoride and OH minus ions. Therefore, we are increasing the OH minus ions, the hydroxide ions that are in solution, and therefore the salt is basic or alkaline. Let's have a look at an application of hydrolysis by looking at November 2018, question 7.2. Question 7.2 says, acid rain does not cause damage to lakes that have rocks containing limestone. Hydrolysis of calcium carbonate, limestone, results in the formation of ions which neutralize the acid. 7.2.1 says, define hydrolysis of a salt. So 7.2.1, hydrolysis of a salt is the reaction of a salt with water. Question 7.2.2 says, explain with the aid of relevant hydrolysis reaction how limestone can neutralize the acid. So let's first talk about the salt. We've got calcium carbonate, and we know that when that ionizes, it's going to form calcium ions plus carbonate ions. Now, this is not how hydrolysis reaction. Remember, how hydrolysis is a reaction of a salt with water. So here I'm just looking at my salt to determine which part of the salt is going to undergo the hydrolysis. If we have a look here, we know that our negative ion always comes from our acid, and so we therefore would have carbonic acid. On the other hand, our positive ion comes from our hydroxide, and so we would have calcium hydroxide there. This is a strong base, and so we know that the calcium ion is going to stay in solution. So what is going to undergo our hydrolysis is our carbonate ion. And so we're going to take our carbonate ion and we're going to react it with water. And then what's going to happen here is one acts as an acid, the other acts as a base. And so this one's the one with protons, so it's going to act as an acid and it donates a proton over. And so we get HCO3 minus, plus if water loses a proton, what's left? OH minus ions. And so therefore we can say it produces hydroxide ions which will neutralize the acid. So we've been speaking about neutralization reactions, and what we also need to talk about is the indicators that go with those reactions. If we have a strong acid and a strong base, we need an indicator that has an endpoint of around pH equal to 7. An example of that type of indicator is bromothymol blue. On the other hand, if we have a strong acid and a weak base, we're going to get acidic salt, and so we need an indicator that has an endpoint of a lower pH, less than 7. An example of that is methyl orange. The last case is if we have a weak acid and a strong base. There we know we're going to get an alkaline or a basic salt, And so our pH is going to be greater than 7. And so we need an indicator that has an endpoint with a pH that is greater than 7. An example of that is phenolphthalein. Let's get into our calculations. When we're talking calculations, we need to be very aware of the fact that we need to deal with a balanced equation. If the equation is not balanced, we can't work with it. We also then remember some of our formulas from grade 10 and 11. Number of moles is equal to mass over molar mass. Concentration is equal to number of moles over volume. Number of moles is equal to volume over molar volume for gases. Percentage yield is the actual yield over the theoretical yield times 100 to put it into a percentage. And the percentage purity is the mass of the compound over the mass of the whole sample times 100 again to get a percentage. Let's have a look at a simulation of a titration. Let's follow the steps. Step 1 asks us to select the type of reaction. So we're going to go with a strong acid versus a strong base. Step 2 asks us what we're going to fill the burette with. We'll fill it with our acid. Step 3, we've got to select the acid and the base. We're just going to go with the first one, hydrochloric acid and potassium hydroxide. Number 4, we need to select the indicator. We know that we're dealing with a strong acid and a strong base, and so we need an indicator with a pH of around 7. So we're going to stick with the one that we know, bromothymol blue. So now we've got everything set up. What's nice in the simulation is you'll see we've got a magnetic stirrer, so we don't need to worry about stirring the conical flask ourselves. The stirrer is doing that for us. Okay, let's use the slider to add some acid into our conical flask. Add a little bit more. We're not seeing any color change. Add a bit more. Okay. I've added quite a bit, so let's add dropwise for a bit and see what happens. And there we go. We have one drop that changed the color from a blue to almost greenish color. So it hasn't gone to the yellow of an acid, that bromothymol blue. The color that bromothymol blue is in an acid, so it's in between the two, and so we've reached the end point of our titration. We would then use the values that we got for the volume of the acid, as well as the volume of the base and the concentration of the base, to find the concentration of the acid. We won't do that today, but if you watch our experiment episode, the calculations are done there. Right, let's have a look at an application question from November 2018, question 7. We've done question 7.1 and 7.2, and we've also done question 7.3.1. It says the volume of water in the lake is 4 times 10 to the 9 decimeters cubed. Lime is added to the water to neutralize the acid according to the following reaction. Lime plus hydronium ions gives us a calcium ion plus water. 7.3.2, if the final amount of hydronium ions is 1,26 times 10 to the 3 moles, calculate the mass of lime that was added to the lake. Right, so we're going to just remove our previous answers. We'll keep 7.3.1 because we're going to need that in this question. Right, so what we need to do is we need to find out how many moles of hydronium ions are actually reacting here. We know the concentration of the hydronium ions initially from question 7.3.1, and we know after this reaction takes place how many moles of ions are left. We know that when we are dealing with calculations, we need to talk about our balanced equation. And why do we talk about a balanced equation? Because we need to know about the mole ratio. So we work with number of moles. So first things first, we need to find out our initial number of moles. We have our initial concentration, And so we are going to find out our initial number of moles. Remember that concentration equals number of moles over volume. And so our concentration is 1 times 10 to the negative 5. Number of moles over the volume, they told us, was 4 times 10 to the 9. And so the number of moles, maybe we should just write here, this is initial, before the reaction. And that is going to be 1 times 10 to the negative 5 times by 4 times 10 to the 9. And so we get 40,000 moles before this reaction took place with the lime. After the reaction took place with the lime, we were left with a number of moles after the reaction as 1,26 times 10 to the 3 moles. And so how many moles were actually reacted? Well, we're going to look at our change in our number of moles. So we started out with 40,000. So we're looking at number of moles reacted, which is going to be our 40,000 that we started with minus what we were left with. And we get out 38,740 moles. Now that we know how many moles of hydronium ion reacted, remember all of this is for hydronium ion. We can then have a look at our balanced equation to calculate how many moles of calcium oxide reacted. We can see that it is a 2-to-1 relationship, so the number of moles of calcium oxide is going to be a half the number of moles of the hydronium ion, which is a half times 38,740. Type that into our calculator and we get 19,370 moles. But we're not done. They asked us the mass of the lime that was added to the lake. We've got the number of moles, and so therefore we can calculate our mass. Remember that number of moles is equal to mass over molar mass, and the number of moles is 19,370. Our mass, our molar mass for calcium oxide, we would have a look at our periodic table. Calcium over here has a mass of 40, where oxygen has a mass of 16, so the molar mass of calcium oxide is therefore 56. And so we can say 19,370 times by 56, and our mass is 1,084720 grams. In other words, if you want to put it into kilograms, it's 1,084,72 kilograms. Some of your calculators might give this in scientific notation. It would then be 1,08 times 10 to the power of 6 grams. Let's have a look at our last application question from November 2019, question 7.3. Question 7.3 says, HBr reacts with zinc hydroxide according to the following balanced equation. An unknown quantity of zinc hydroxide is reacted with 90 centimeters cubed of hydrogen bromide in a flask. Assume that the volume of the solution does not change during the reaction. The excess HBr is then neutralized by 16,5 centimeters cubed of sodium hydroxide of concentration 0,5 mole per decimeter cubed. The balanced equation for the reaction is given. 7.3.1. Calculate the pH of the HBr solution remaining in the flask after the reaction with zinc hydroxide. So what we want to do is we need to have a look at the pH of HBr. In order to get the pH of HBr, we need to know the concentration of HBr. In order to know the concentration, we need to know the number of moles. Luckily, we have a balanced equation, and so if we can find the number of moles of sodium hydroxide, we can use the balanced equation to get the number of moles of hydrogen bromide. So we're going to start with our sodium hydroxide. And so what do we know about the sodium hydroxide? We know that we have a volume of 16,5 centimeters cubed, which in other words is 16,5 times 10 to the negative 3 decimeters cubed. Remember, we always need to work in decimeters cubed, and so we divide by 1,000 to get there. Another way of writing divide by 1,000 is times 10 to the negative 3. We also know that the concentration is 0,5 moles per decimeter cubed, and we want to find the number of moles of NaOH. We know the number of moles is equal to concentration times volume, and so we substitute in 0,5 times the volume of 16,5 times 10 to the negative 3, and we're going to type that into our calculator. 0.5 times 16.5 times 10 to the negative 3, and so we get 8,25 times 10 to the negative 3 moles. So now we have our concentration of sodium hydroxide. From our balanced equation, we get that is a 1-to-1 relationship, and therefore the number of moles of HBr will equal the number of moles of NaOH, which is 8,25 times 10 to the negative 3 moles. So our concentration of our HBr, concentration equals number of moles over volume, and so we're going to have 8,25 times 10 to the negative 3 over our volume of HBr, which remember was 90 centimeters cubed, but we can't work in centimeters cubed, so we need to times by 10 to the negative 3, or in other words divide by 1,000, and then we've got 8,25 times 10 to the negative 3 over 90 times 10 to the negative 3, and we get an answer of 0,0916, etc. And we know that the concentration of the acid will be equal to the concentration of the hydronium ion. Why is that? Well, because it is a monoprotic acid, and so every mole of acid produces 1 mole of hydronium ion. And so we can use our concentration of our acid to find our pH, and we say negative log of 0,0916, etc. And luckily we still got that there on our calculator, so we say negative log of the answer, and that's equal to 1,04. So the pH of this solution is 1,04, which does sound correct because we know we're dealing with an acid, and it's quite a strong acid, so we should have a very low pH. Remember, with this scenario, if this was a diprotic acid, that would mean for every mole of acid you would get 2 moles of hydronium ion, and then your concentration here would not be equal. We would need to double up to get the concentration of our hydronium ion. So that's the answer to question 7.3.1. Let's have a look at question 7.3.2. Question 7.3.2 now says, calculate the mass of zinc hydroxide initially present in the flask if the initial concentration of HBr was 0,45 moles per decimeter cubed. So now we're having a look at our first reaction. So first things first, in order to work out about our zinc hydroxide, we're going to need to find our number of moles of HBr that reacted in this first reaction. From question 7.3.1, we know what was left over. The 8,25 times 10 to the negative 3 moles was left over. It was in excess. That's what reacted in the reaction 2. And now we also know the concentration of the initial, so we can find out how much we started with, how much was left over, and therefore how much reacted in between. So let's start with that. 7.3.2. We're looking at initially our number of moles of HBr is going to equal concentration times volume. The initial concentration, they told us, was 0.45. The initial volume of HBr was our 90 centimeters cubed, so it's 90 times 10 to the negative 3. And so we're going to type that in, 0.45 times 90 times 10 to the negative 3. And we get 0.0405 moles that we started with. We also know that what did we have in excess, what was left over and used in reaction 2, that was what we got over here, the 8.25 times 10 to the negative 3. And so what actually reacted would be what we started with minus what we left over with. And so we get 0.03225 moles that reacted of HBr. And so then we can look at our balanced equation to get the number of moles of zinc hydroxide. And if we have a look at our mole ratio, it's a 2 to 1, so there's half the amount of zinc hydroxide, so half of our number of moles of HBr. And so it's a half times 0.03225. And so we get 0.016125. And then finally they actually asked us for the mass of zinc hydroxide, so we're going to say, well, number of moles is equal to mass over molar mass. And so our number of moles is that 0.016. The mass is what we're looking for, and the molar mass we're going to get from our periodic table. Bring this across. Zinc has a mass of 65, plus we've got 2 oxygens. Oxygen is 16, plus we've got 2 hydrogens. Hydrogen has a mass of 1, and so we get a molar mass of 99. And so we're going to take our previous answer there. We can actually get to our previous answer on our calculator, times by 99. And we're going to get a mass of 1,596. So we round off 2 decimal places. It's 1,60 grams. That brings us to the end of question 7 for November 2019, and it also brings us to the end of Acids and Bases Part 2. We look forward to seeing you for the next episode.